Right? So we're going to learn about the combinational circuit, okay, and the case study, which is the example in the real world. Okay. There are two types of circuits, which is the combinational circuits, and the other one is the sequential circuit. Okay. Combinational and sequential circuits. Right? And what is a combinational? Combinational is, okay, where you have inputs and then there's the circuit, combinational circuit, and then you have output. Okay, so the output is depending only on the input. Okay. Comparatively, the sequential circuits we have a combinational circuit in the sequential circuit. Combinational circuit, input, output, and then some of the output is bring to the memory and going back as input. So it has a feedback. Okay? A circuit that contains a memory for a feedback is called the sequential circuit. This is what we're going to learn next week. Okay? This week we're going to learn about combinational circuit. Okay? Example for combinational circuit, okay? Adder, multiplier is basically an adder, comparator. Example for sequential circuits, those that basically has flip-flops. Okay? Latch, gates, and so on. Latch gates. Okay? All right. So that is about the combinational circuit. Now, our content today, we have 6 parts. The first part is to see the design procedure of combinational circuit. Okay. And then BCD adder. Hope you can see it, although it's quite blurred. BCD adder, and then binary to BCD converter. Okay. Barrel shifter, comparator, and incrementer. Right. So the first one is about the BCD adder. Right. Sorry, the first one is about the design procedure. Sorry. Okay. So the design procedure for combinational logic. Okay. First, we have to know the specification. What is the specification? It is what are the inputs, what are the outputs. Okay. That's the specification of the combinational logic circuit. Okay, because remember, the outputs are depending on the inputs. So we need to know what are the outputs, what are the inputs, okay, how many bit of the output, how many bit of the input. So that is all the important specification. And then when we have the specification, we have to do formulation, which is we have to derive the truth table or the Boolean equation, okay, which define the required relationships between the inputs and the outputs. Okay, so these are the SOP and POS. Okay. Either it's through truth table or through K-map. All right. And then we have to do optimization, which is to apply two-level or multi-level optimization. This means we have to consider the hierarchy, modularity, and another one, regularity. Okay, hierarchy, modularity, and also the regularity. And then once we got the optimized circuit, optimized formula, we can start with the design entry, which is using schematic or using the hardware design language, okay, which is the Verilog. All right, and then we try to compile it and do the technology mapping, which is to transform the logic diagram to a new diagram using the available implementation technology. So this means the library. Okay, the new diagram means the netlist. The netlist. Yeah. Because we want to make it, okay, from just design on a software, we want to make it a hardware, but to fabricate, okay, to make it a hardware, we have to know what are the technology that we have. Okay. Of course, right now we have the 5 nanometer transistor technology, like the PS5, but do we have that resource in our country? Do we have that resource in our company? Okay. In UTM, for study purpose, we only has as low as 32 nanometer. Okay, 32 nanometer. All right. And then when we have designed it with the technology, okay, we will do the verification, which is to verify the correctness, okay, the functionality, and the delay, okay, through the waveform and everything. All right. So that is the design procedure for the combinational logic circuit. All right. Now the next one is the BCD adder. Okay. What is the BCD? BCD is binary coded decimal. Okay. Binary coded decimal, where we are basically implementing decimal in binary. Okay. So BCD can only, okay, what you have learned in first year, right, in digital electronic, BCD can represent 0 to 9, right? Which actually mean BCD is representing 1 decimal digit. 1 decimal digit. All right, but why we need BCD adder? Okay, must have thought of that. Why we need BCD adder? We have many types of adder already. Why we need BCD adder? Okay, who wants to apply the BCD adder? So BCD adder is actually like you are adding not decimal number itself. You are not adding the binary. Okay, the computer, the hardware will add using binary. Okay, but you want the answer to be in decimal. Okay, of course, if you use binary, in the end you will convert it back to decimal, right? But some applications, okay, especially in commerce and finance, they want it as in the decimal. Okay, are there difference? Yes, there is. Okay, because in binary, okay, uh, in binary, especially when we do fractions, in binary fraction, we have error, right? We have error. For example, let me think of a good example. For example, if we have 0.6 in decimal, so right, 10 in decimal, how do we convert this to binary? How do we convert this to binary? Of course, we're going to use 2 to the power of 1 plus 2 to the power of 3. So this is 0.5 and this is 0.125. So this is actually 0.101 in binary. But this is actually 0.625. And in applications such as finance or commerce, okay, this error is not acceptable. Of course, in binary, we can truncate. We can truncate and we can do truncation, we can do round, but we still have a little error, right? As what we learned in chapter 4, chapter 3, chapter 4. Yeah, chapter 4. Okay, truncate and round, we still have error. But in finance and commerce, those errors are non-negligible, not accepted. So the finance and commerce people want to calculate using computer, but the answer must be precise as in the decimal calculation. So that is where we need the BCD adder, right? That is where we need the BCD adder. Okay, so now let's see the problem with the BCD. Yes, we can implement BCD. We have representation from 0 to 9, remember? Okay, but what's the problem? Okay, when we add two BCD representation, okay, it is fine. It is fine when we have the answer as 1 decimal digit. But it is not okay. Okay, it is not okay if the answer is more than 1 decimal digit. So here in the example is 2 decimal digit. Okay, let's see. 6 plus 3 is 9. 9 is the correct representation in the BCD, okay, which is 1001. Right? 5 plus 7 is 12. And 1100 is not the correct representation of 12. Okay, so how can we represent the BCD numbers that are more than 9? Right? Okay, let's say the 12. Okay, 5 plus 7 is 12, but it is a non-BCD. 1100 is non-BCD. Because this BCD is a 4-bit that represent from 0000 to 1001. Okay. So we need adjustment. What are the adjustment? We add 6. We add 6 every time. Okay. Add 6 every time. All right. So what we got then? We got 10010. And this one will represent the 10th in the decimal. And this 0010 will represent the ones in the decimal, okay, which is 1 and 2. Right? Okay, let's see another example. So how do we represent 15? We add 6 to that. Now that we add 6, we have, okay, the correct BCD, which is 1 and 5. All right. Other example, 18. 18. Okay. Now that we can use 5-bit, which means we can represent more than 15. Right? So the correct BCD for 18 in BCD is, we have to adjust by adding 6, and there's 1 and 8. Right? Okay, so this is all the table. Oh yes.
Why we only add 6, not 5 or 4, 7? Why only 6?
So the mathematician has found it for you. So we just use. So if you add 4, is it going to be correct?
No, I didn't try, but why only 6?
Because the mathematician has found it for you. They have tried and error and they have found it for you. So we don't have to worry about the mathematics behind it. Okay? Just use add 6. Right? We're not
Right.
mathematicians. We're engineers, right? Okay, so now here is all the possible adder output in the BCD adder. Let's see, we have 19. Why 19? Because okay, you have input A, you have input B. Okay, these two inputs is going into BCD adder and it will generate a BCD sum. Right? So we have A input which is 4-bit and then B input which is 4-bit, right? Because those are BCD. So A can represent B in the correct way, okay, from 0 to 9. Same goes to B. B can represent from 0 to 9. Okay, so A plus B, A and B represent can be in the range of 0 to 18. But if we consider okay, the carry, we consider the carry, that is plus 1. So it's 0 to 19. Okay, that's why we see 19 representation here. All right, so let's see the first part of this truth table. Okay, the first part, so we have decimal here. So this is the binary sum. Okay, when we add A and B as a normal, using normal binary adder, so this is the answer that you will get. But this is the actual answer that we want, which is the BCD sum. Okay, for 0 until 9, no problem. This and this, all this, oh, I'm not sure if you can see it, all this and all this are equal. No problem. Okay. Now let's see the bottom part of the truth table. Okay. When we have answer from 10 to 19, when we have answer from 10 to 19, okay, these are the 2 decimal digit. So as the mathematician has found for us, we need to bias 6. I mean, we need to add 6, okay, to the binary. Okay, so if you want to, if you want to design a circuit, okay, if you want to design a circuit, okay, let me erase this because I want to use that circuit. Before getting our BCD sum, so let's say this is a binary adder, normal binary adder. So we will get binary sum here. Okay. Now we want to design a combinational circuit here, okay, to get binary sum. Sorry. Oh, sorry. It's BCD sum. Let's change the color. BCD sum. Okay. So what are the process here? It's plus 6 to, okay, not all. We only plus 6 to this part of the truth table. To 10 to 19. All right, so from the results, we need to recognize 10 to 19, and then we only add 6 to that number. Okay, if the results given is 0 to 9, we're not going to add 6 to that. Okay, if it's 0 to 9, we're just going to straight bring it to the final BCD sum. But if it is 10 to 19, okay, we need to add 6 to that, right? So how can we do that? Okay, we check the truth table and we look the characteristic of 10 to 19. Okay, so how to check the characteristic, right? We can see the difference from the binary sum. Okay, the difference between this number and this number. Okay, so the binary sum number that must be added by 6. Okay, they have C equal to 1. Okay, so when the binary sum has C equal to 1, we have to add 6 to it. Because here, all the C is 0. So when C is 0, we don't want to add 6 to that. Okay? But what about this? Oh, sorry. You don't see my my arrow. I'm sorry. Okay. Here, when C is 1, we will add 6 to this number. 16, 17, 18, 19. We will add 6 to this number. Okay. Because as you can see, from 0 to 9, okay, C is 0. So we will not add 6 to this number. Okay, because this number is excluded lah from this condition. Condition C. Condition. Yes.
May I ask what is that
Yes.
C means?
Carry.
C is that C in or carry in, right?
Carry out.
Oh, carry out. Oh.
Carry out.
Oh, thank you.
Sorry. Okay, no problem. Condition to add 6. Okay. One condition, C must be 1. And this will cover 16 to 19. Okay. And now we have exclude the 0 to 9 because all C from 0 to 9 is because all C value of 0 to 9 is 0. Okay, all the carry out value is 0. Okay, so what about 10 to 15? They are also having 0 carry out, right? So now we have the second condition. We have to check second condition where both S3 and S2 is 1. Okay. None others have this condition. None others. Both S3 and S2 is 1. None others, right? Only 12 to 15. So S3, S2 must be 1. So this will cover 12 to 15. And then what about these two? 10 and 11. So we have to find another only characteristic for them, right? So the third one is when S3 and S1 is 1. Okay, right? Because that's the only characteristic that they have that is not equal, that is not the same with the others. Okay, for 10 and 11. So S3, S1 is equal to 1. So this will cover 10, 11. Okay, so we can say that this circuit, okay, is C plus S3, S2 plus S3, S1. Right? Okay. Okay, any question so far? All right, if no question, then I will proceed. Okay, correction factor using truth table. All right, when the sum exceeds 9, carry bit C is 1 or, okay, so this is one condition that we talked earlier. So carry bit C is 1 or the binary sum is between 0101 and 1111. So this is 10 and 11. So between 10 to 11. So draw a truth table of S1, S0, S1, S2, S3. Okay, you don't have to include the C for this case. Okay, for this case, you don't have to include the C because we only choose the C that is 1. All right. So we have clear with the C, the condition of C. Okay, now we want to check the condition of S0, S1, S2, and S3. Okay, so the binary sum must be between 10 to 15. So we only fill 10 to 15. Okay, 9, 10, 11, 12. Betul ke? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, 10 to 15. Okay, fill it once and find the group, and then okay, the group is represent S3, S2 and S3, S1, but the first condition is C is 1, so we add C. All right, we add C and we call it as K. K. All right, K is 1. Okay, when all this is 1, C, S3, S2, S3, S1 is all is 1, then it will produce 1. So that 1 is for K. Okay, the bias K. And K here is 1 at 10 to 19. Right? So we call this circuit in the cloud here as K. K is equal to C plus S3, S2 plus S3, S1. All right? Okay. And then we implement the circuit. So we have initial carry or carry 0, and then add in just the A, and then the B, and then we have the carry out. So C, so this is the C, and then this is S1, S3, and this is S2, S3. Okay? And that will connect SK, and when this is detected, when this is 1, okay, we will give that 1 to this value. Okay, this wiring here says, okay, 0 is connected to here and here. 1, okay, the answer from K is connected to here and here. So this will be a new input of a new 4-bit binary adder, which is 6. So this is 6, and this is the S3, S2, S1, S0. Okay, so when S3, S0, S1, S2, S3 is 0 to 9, okay, K is equal to 0, okay, because the conditions are all not satisfied. So K is 0, so we will only add S0, S1, S2, S3 with 0, okay, because K is 0. When K is 1, we will add it with 6, and that will be our BCD sum. Okay, it's that simple. Alright. So that is how we create the combinational. Okay, logic circuit. So this is the BCD adder, basically. Now we want to see the other way to convert the binary to BCD. Okay, binary to BCD. Okay, one algorithm to convert the binary to BCD is called the double-double algorithm. Okay, in this algorithm, we are converting n-bit binary number. Okay, n-bit binary number to BCD. Okay, how to do it? First, we find the number of bits which hold the biggest BCD outputs. I think this means if we have 0, 0, 1, 1, 1, 1, 1, 1, for example, so n is 6 bit. Okay, this is not count because it's not significance. All right. And then we divide the output into BCD columns of 4 bits each. Oh, BCD columns means we want to see the hundreds, tens. I don't know how to say how to spell. Maybe like that. Tens and the ones. All right. And then we shift the binary number 1 bit. And if the binary number, if any of the BCD columns is 5 or greater, okay, we add 3. Okay. In this circuit, okay, we find the binary sum and then we add 6 to the binary sum. Okay. But here we want to check bit by bit, shift bit by bit. So we add 3. Okay, if it is 5 or greater. Okay. 5 or greater. Okay, add 3 to the BCD columns. And then repeat from step 3 until all n bits have been shifted. Okay, repeat step 3. All right. Let's see the example so that we can see it clearly. All right. So we have 3F in this example. So 3F is 0, 1, 1, 1, 1, 1, 1. Oh, my example. Okay. Oh, so this is using the double-double algorithm. Okay. So 3F is 0, 0, 1, 1, 1, 1, 1, 1. So that is in hexadecimal. Okay. The binary that is significant for the BCD is 1, 1, 1, 1, 1, 1. That is 6 bit. Okay, so we have to shift 6 times, right? Okay, let's shift it one by one. Okay. So the step 2, we say divide the output into BCD columns of 4 bits each. That means 4 bits of ones, 4 bits of tens, and probably 4 bits of hundreds. All right, so that is what it means. Okay. I'm not sure if some of you who are Malaysian, who's learning Malaysian school. I'm not sure if you are learning math and science in Malay or not, but at my time, we learned it in Malay. We call this rumah sa, rumah puluh, and the other one is rumah ratus, right? Ones, tens, and hundreds. Okay, so we have 3F. 3F is 1, 1, 1, 1, 1, 1. And first, we shift it 1 to the left, okay, into the BCD column. Okay, we shift it 1 to the BCD column and check. Now the value and the BCD column is it bigger or equal to 5? No, it's not. It's 1. Okay, so we shift another one. Now is it bigger or same to 5? No. So we shift another one. Now, okay, this is 7. So it is bigger than 5. So we add 3 to this number. And 7 plus 3 is 10. So we got 10 here. Okay, after that, we shift. Okay, we shift this one here, and of course that will affect this one here because each column has to have 4 bits, right? One here, one here. All right. Now we check. Is this equal or bigger than 5? Yes, it is. It is 5. So we add 3. We add 3. So this is 5. 5 plus 3 is 8. So we have 8 here. And then we shift again. Shift. All right. Now we have 3 here and 1 here. Okay. And we still have another 1 bit binary left. So we shift another one. Okay. And we stop because we have shift all the binary bits. Okay. So the BCD is 1100011 or 63 in BCD lah. So BCD is the binary part. So this is the BCD value. Okay, this is the equal in decimal. Okay, 63. So you can check, is 3F in BCD is 63 in decimal? Yes, it is. Okay, you can check. Okay, that is the example of 6-bit. Now let's see example of 8-bit, okay, which is bigger, longer BCD. So with 8-bit, we have another column for the BCD, which is the column hundreds, right? So we do the same. We shift, okay, check if it's 5 or not. And if it is 5 or bigger, we add 3 and then we shift again. Shift again. And if it's 5 and bigger, we add 3 and then we shift again. Okay. And then, okay, if it's 5 and bigger, now it is 5 and bigger at column tens. Okay, so we add 3 to this column only. To this column only. Do not add 3 here. Add 3 to this column. Okay. We add 3 to this column only because this is the column that is bigger than 5. Okay, bigger or equal than 5. After we add 3, we shift again. Okay. When we shift here, it will affect here. So we shift all until we have shift everything. Now we have shift everything. Okay. The final results is 5. Here, 5. 5. All right. 2. But we don't have to add 3 because we have finished shifting all bits. All right. See? Repeat from step 3 until all n bits have been shifted. Okay. Once all bits have been shifted, we stop. Okay. We don't have to go back to 3. Stop when all bits have been shifted. Okay. So that is how we got, okay, the BCD is 1001010101, which is 255. And probably you know that is true, that FF in hexadecimal is equal to 255 in decimal, right? Means 8-bit all ones. Okay, so that is the design. Okay, that is the design, which is to add 3. Okay, now we want to make the add 3 as a module circuit. Okay, we want to make the add 3 as a circuit module. Okay, hold on. I forgot to do something. Give me 5 minutes. 4 minutes. Now is 8:56. We start again at 9.
Okay, doctor.
Right. Okay. Let's start again. Let's start. Let's restart. So your test, which is next week on 28th. So far it's next week, right? Yeah. So far there's no news yet, so I'm a bit worried. So I cannot promise you that the question is easy. Okay. But yeah, you have to try your best. It is up to this chapter, the combinational logic design chapter. But basically, if you see the previous test, it is up to like multiplier. But you still have to understand about this chapter. It's just that it is quite hard to make question from the chapter 6, the combinational logic design case study, because we only studying the case study, which is the circuit that has been designed. Okay, we're not designing a new circuit. So chapter 4, 3, 2, 4, 5, 2, 3, 4, 5, we can ask you to design a new circuit or ask you to calculate the CPD and everything, but I'm not sure how they're gonna make a question from this chapter. Okay, chapter 6. All right, back to this, which is the add3 module. So previously we have seen how we can add 3. Okay, we can use add3 to convert a binary number to BCD. Okay, we use shift and add3, shift and add3, right? So this add3 can be made as a module, okay, but we call it a 4-bit conditional adder because we only had 3 on certain conditions. Right? So what are the conditions? So let's see the truth table here. Okay. For this design, for the CADD design, we only add 3. Okay. When the input means this input. The input B0 to B3 here. The input is between 5 and 9. Okay. And if the condition is between 0 and 4, we add 0. It will only pass through. Okay. It will only pass through the adder, the C add 3. Okay. If it's 0 to 4. And if it's between 10 to 15, we do nothing also. Okay. We don't care. Right? Now let's see an example. So we have 2 design. Okay, for this type of C add, we have 2 design, which is for 6-bit binary, which is when we want to convert 6-bit binary to 2-digit BCD. 6-bit binary to 2-digit BCD. And remember, you might think, why is it like this? What is the algorithm behind this? It's not about the algorithm. This is a fixed design. Okay? It is a fixed design, okay, fixed circuit design to convert 6-bit binary to 2-bit BCD. Okay? It's a fixed design. Remember, it's fixed design. So you don't have to find out what is the mystery behind this, the algorithm behind this. It's fixed. It's like that. Okay, so let's see the example here. So we have 1 1 1 1 1 6-bit of 1 here, 1 1 1 1 1 1. Is it? Yeah, it is. 6-bit of 1 here. First, we have to shift this 1 place to the right and make the MSB 0. That is the step 1 on using the combinational add3, C add3. Then make the first 4 higher order bit as the input to the CAD. So this is the first 4 higher bit, 0 1 1 1. So this is the input to the C add3. And then is it? If it is between 5 to 9, we add 3. Right? If it is 0 to 4, just pass through. Okay? And if it's between 10 to 15, 10 to 15, ignore. Okay, mostly it will never happen. All right. So now it is 0 1 1 1, that is 7. So we add 3. So 7 add 3 is 10. So we have 1 0 1 0. And then we shift 1 bit and make 0, 1, 0, and then 1 from here, 1 from here to be the new input of the C at 3. And this one here is bring to the BCD output, right? And then this value is 0, 1, 0, 1, 0, 1. So that is 5, which is in this range. So we have to add 3. So 5 add 3 is 8. So now we have 8. 1, 0, 0, 0. And then this one is bring to the output, and we add 0, 0, 0, and this one, okay, to the new C add 3. Okay, so now we have 1, okay, 0, 0, 0, 1. So that is 1. So it's in this condition, in range. So we just going to do pass through the adder. So we will get 0, 0, 0, and 1. And then the last digit, which is the LSB, is bring to the output. Okay. And since we want 4-bit, 4-bit, we add 0 at the MSB. Okay. So that is how the circuit is designed. Okay. You can try this. You can change this with any 6-bit binary number, and you will get the correct BCD number. All right. So for this case, so 111111 is 3F, which is 63 in decimal, which is correct. So the BCD representation of it is 01100011. Right. So that is a 6-bit binary. So this is just a case study. It says it's just an introduction for you to circuits that are used in the real world. Okay. So that is for 6-bit to 2-digit BCD. Now we want to see 8-bit binary to 3-digit BCD. Okay. 8-bit binary to 3-digit BCD. Okay. Sorry, let's go back. So now in this circuit, okay, we have a few wires, and also our wires have not much power or delay consumption, so it's okay. We just have 3 C at 3. Okay, we have 3 C at 3 circuit modules. Okay, modules. We call these at 3 modules, right? At 3 modules. Okay, so for 6-bit, we have 3 at 3 modules. Let's write it there. Right. Now, for the 8-bit, we have 1, 2, 3, 4, 5, 6, 7. 7 at 3 modules. Of course, bigger, longer bit will have more complex circuit. So this is the fixed circuit. Remember, this is a fixed design of fixed circuit, or we usually call it as architecture. So it's a fixed architecture. Okay, for the 8-bit binary to 3 BCD digits. Right. Okay, so first we do the same. We have 1111, 8-bit of ones, and then we put 0 at the MSB and put that into the C add 3 module. So this is 7. So we add 3 here. We add 3 here, and that will produce 1010, which is 10. 1 is bring to the next stage, and then here we add 0, 1, 0, and this one here to the C at 3 module. Okay, and this is 5, 5, right? Yeah, 5. So we add 3 here. I should have put it inside. So we add 3 here. Okay, and 5 plus 3, that is 8, 1, 0, 0, 0. So the MSB is bring to another stage, and now we are bringing the next bit 1 down here. So now we have 1. Okay, 1. We just pass through, which is at 0. So now we have the answer for this C at 3 is 0, 0, 0, 1. All right. So now here, okay, in this architecture, we have another 2 C at 3 at this level. We have C at 3 here, and we have C at 3 here, which is this one is for the MSB that has bring to the output, okay, which is 0, 1, 1, 0, and then 0, 0, 1, and another, sorry, oh, yeah, another one here. Okay, so this is 6, 6, so we add 3, and this is 3, so we add 0 here. So this one will pass through, only pass through as 3, and this is 6, 6 plus 3 is 9, so we get 1, 0, 0, 1, which is 9. All right, and then we have another pair of C at 3 here. Okay, we have another pair of C at 3 here. And this is 0, 0, 1, 0, which is 2, so we just pass through. And this is 0, 1, 1, and 1 here, which is 7. So 7 plus 3, that is 10, which is 1, 0, 1, 0. And the LSB is bring down to the output. Okay, and make it 4 bit each. So it's 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1. So that is the fixed architecture. Okay, you can change this to any 8-bit binary, and you will get the correct BCD. Like for this, FF, which is all ones in 8-bit, will produce 255. Okay, you can test with 0, 1, 0, 1, 0, 1, 0, 1, which is 55 in hexa. So you get 0.85 in decimal, or 10 in decimal, 10. Or you can try CC in hexadecimal, which is 11001100, and you should get 204 in decimal. All right, so you can try it later. Now let's see the implementation. Okay, so now we can improve our BCD adder. Okay, instead of having input A, input B, okay, going into 4-bit binary adder, okay, and then sum of A going into the combinational circuit to calculate K, and then go to the another adder and get the sorry, not binary, BCD sum. Instead of having this circuit, which is okay, Sorry for scrolling fast. Okay. Instead of this circuit, now we can improve this circuit to become like this. Okay, to become like this. So inside the C at 3 here, so this is like a big C at 3. Okay. And I have introduced you the design for 6-bit and 8-bit. Okay. We're not going to see the details on that because I'm not sure if the research has been done truly or not. But it is said that this circuit is much more efficient than the original circuit that we learned previously. Okay. All right. So that is about the BCD. Now we're going to see the next case study or the next example of combinational logic, which is the barrel shifter. So it's just a shifter. All right. So this is a generic barrel shifter. Okay. So why we need a barrel shifter? So instead of shifting 1 bit at a time, okay, we want to shift multiple bit at a time. We want to shift multiple bit at a time. So barrel shifter can shift, or maybe we say rotate, multiple bit at a time, right? And there are 2 types of the barrel shifter, which is the crossbar type and also the logarithmic type. The crossbar type is quite complex, so it is quite hard to do that in class. So we just choose the logarithmic barrel shifter, which use log2 n stages to shift n bits. All right. And in the generic barrel shifter, we have n bit input, n bit output, and the amount to be shift is log2n, and we can also have a few mode selections. Right. Okay. Now this is an 8-bit barrel shifter. This is an 8-bit barrel shifter. Okay. So this is the input and this is the output. Okay. So this is the shift amount. Okay. We can shift for 8-bit, we can shift it 0 times, which means we don't shift it until 7 times. Which means this is 1, 1, 1, right? We can shift it until 7 shifts or 7 rotates. So when we shift 1 time, X7 will go here and the rest will shift to the left. So that is how we shift or rotate. Okay, barrel shifts. Okay, barrel is round, right? So it's like we shift it in a round. So it's like a rotation. Okay. So this is one shift. Let's write it like this. Okay. So we have X7 to X0. We shift that 1 time. We will have X6 to X7, because now X7 has rotate to the position of x0 here. Okay, so now we have x6 to x7, and then we shift again, which means we shift this 2 times. We have x5, x6. Okay. Now we try to shift it again. We have x4, x5. Right? Shift it again. x3, x4. Shift that again. x2, x3. Okay. Shift it again. x1, x2. Okay. Shift it again. x0, x7, which means we totally shift this position. Okay. x0 go to x7, and then x1 go to x6, x2 go to x5, and so on. So this is shift 1 time. Okay. Shift 2 time. Shift 3 time. Okay. 4 time. 5 time, 6 time, 7 time. All right. So let's see. If we shift 0 time, which means we don't shift at all, we will get the exact y7 to y0. Here the output. We will get the same value as the input because you didn't shift at all. So x7 to x0. Okay. x7 to x0. If we shift it 1 time, we will get, oh sorry, not this one. We got here. Okay. x6 to x7 here. If we shift it 2 times, 1, 2, we got it here. Okay. We got this value, x5 to x6. Okay. If we shift it 4 times, 1, 2, 3, 4, we got this one, x3 to x4. If we shift it 7 times, so it's this one. We get x0 to x1. Sorry, not x7. Yeah, correct. x1. Because it's this one. Okay. This one is going here. x1. Right? So that is about the barrel shifter. Okay. So this barrel shifter, okay, can be implemented using 8 to 1 marks. Okay. Since any bit can go to any position, okay, which means we do full rotate. Okay. When we do full rotate, any bit can go to any position. So we can implement it using marks. Like if we want to shift it how many times, then x will become, okay, x7, okay, let's see. Okay, if we shift it 1 time, x7 will go to 0. Okay. If we shift it 1 time, like 0, 0, 1, okay, x7, okay, x7, what is this? y7, or y7 is equal to, if we shift it 1 time, y7 will equal to x6. Okay. y7 will equal to x6. Okay. If we choose, and y6 will be, if we choose to shift 1 time, y6 will be x5. And so on. Okay, and so on. So we can have 8 to 1 multiplexer. Use 8 to 1 multiplexer. So, inside 8 to 1 multiplexer, inside each of the 8 to 1 multiplexer, we have 1, 2, 3, 4, 5, 6, 7, 7 2 to 1 mux. Which mean here we have 7 by 8 2 to 1 mux, which is 56 2 to 1 mux. Alright, so knowing this architecture, knowing this design, we can improve, okay, we can improve the circuit. So this is inside of 8 to 1 multiplexer. Okay. So instead of using 56 8 to 1 mux, we can share the intermediate mux, okay, and have 1, 2, this is 8 by 3 is 24. So 24 2 to 1 mux, okay, instead. Right? And this is a modification to make the 8-bit barrel shifter to be more efficient. Right? So you can check the circuit later. Now, I want to introduce comparator. Now is 9:30. Yeah, we have time. So my target is to finish all of this chapter today, but it's not a hard chapter. It's just like introduction of this algorithm and introduction of these circuits. It's just a case study. Okay, but it is good for you to learn about the current combinational circuits in order for you to get an idea how to design a combinational circuit, which will be in the test. Okay, to design the combinational circuits, not this exact circuit, but how to. Okay, you have to get to know the how to. All right. Okay. The how to is not like what Anas asked just now, like why at 5 or why at 6, not 4 or 5. It's not that. I mean, like, when we have 8 to 1 marks, okay, instead of 8 to 1 marks, we can optimize it using 2 to 1 marks. But if we want, because 2 to 1 marks is much simpler than 8 to 1 marks. But if we want to use 8 to 1 marks, that will cost us 56. Okay, 56 2 to 1 marks. 2 to 1 marks. Sorry, this is a mistake. Okay. And from the 56, we check if there is a common marks that we can share. And yes, we can share the intermediate marks to make it only 24 2 to 1 marks. So that is the how to when we design a circuit, right? Okay, next circuit that we're going to see is the comparator. So in digital electronic, you have seen a magnitude comparator, okay, the IC of magnitude comparator, where we compare 4 bits with a 4 bits to see if input A is bigger than input B, or input A is equal to input B, or input A is less than input B. Okay, so this type of comparator is a I don't know how to spell parallel. 1L, 2L, but it's a parallel. Okay, it's a parallel comparator where it compare all bits at once. Okay, it compare all bits at once. How can the IC compare all bits at once? It has the equation. The equation is if x3, x2, x1, x0 is equal to 1, or if x3, x2, x1, x0 is true, then E is equal to 1. E means A is equal to B. Okay, input A is equal to input B. Right? And then if this condition met, means A is less than B. Okay, which means L, output L here is 1. Okay, and if this condition met, okay, which means that means A is bigger than B. Means output G is equal to 1. Okay, output G is A is bigger than B. A is greater than B. Okay, G is for greater, L is for less, and E is for equal. Okay, we have A3, A2, A1, A0, B3, B2, B1, B0 here, but in the equation we have X. What is X? X is XNOR. XNOR relation between A and B. Okay, let's see what is it. Okay. XNOR says when two input is equal, okay, we will produce 1. If not, we will produce 0. So that is XNOR. Right? That is XNOR. So XNOR is X. So in the E equation, the equal equation, we will check the XNOR of each bit pair, which means we compare A3 with A3, A2 with B2, A3 with B3, A2 with B2, A1 with B1, and A0 with B0. Okay, we compare that. So if X3, which is A3, B3, the XNOR of A3 and B3, okay, is 1, is equal, whether it's both are 0 or both are 1, okay, then X3 is 1. Okay. And then if A2 and B2 is equal, which means if both are 0 or both are 1, this is also 1. X1 means if A1 and B1 are both 0 or are both 1, which is equal, so this is also 1. And X0 means A0, okay, XNOR with B0. If both are 0 or both are 1, that will produce 1. Okay, then okay, E is 1. Okay. All right. So when we compare, we have to compare from MSB. Have to compare from MSB. Right? So if MSB is equal, then we go next. If it's not equal, then we will check if it's bigger. We will check the next bit. If it's bigger or less, or if it's greater or less. Right? So that is how we check the L and G, less or greater. Right? If X3, If x3 is equal, then we check x2. If x2 is also equal, then we check x1. If x1 is also equal, then we check the a0 and b0. Okay. If x3 is not equal, then we check a3 or b3. If x3 is equal, then we check a2 and b2. Okay. If x3 is equal, x2 is equal, then we check a1 with b1. And then if x3 is equal, x2 is equal, x1 is equal, we check a0 and b0. Right? So that is how we check for the less. Okay. If a3 is 0 and b3 is 1, if a3 is 0 and b3 is 1, which means a is less than b, then this value, this term is satisfied and L is equal to 1. Okay. If not, check, okay, when x3 is equal, we check if a2 is less than b2. If this term is satisfied, then L is 1. Okay. So these terms, okay, is the SOP, means if one of the terms, okay, between the plus sign here is satisfied, okay, we will produce L equal to 1. Same goes to the G. Okay, same goes to the G. But G is checking if A is bigger than B. So that's why you see we have prime on the B, okay, for G. All right? Okay, so now let's bring this equation to the next page, which is the 4-bit equality comparator. Okay, where we only want to check if A is equal to B, the equality comparator. And for 4-bit, right? Okay, for 4-bit, we only need 4 XOR, okay, because each of the x3 is, if each of the x is the XNOR of A and B. Okay, it's like this: A2 XNOR B2, okay, A1 XNOR B1, and so on. All right. So the circuit will look like this, where we have 4 XNOR, and the results of the XNOR, which is the X, will go into an AND gate and will produce E. Right? So that is the equality comparator circuits. And for the 4-bit comparator, okay, which is whether it is less or greater. Okay, this is what the circuits looks like, and here we have the XNOR. We have the XNOR. Okay, but instead of using the XNOR symbol, we use this circuit, okay, the normal AND and inverter circuit, because we also need to use the other value, which is this is A3 bar B3, and this is A3 B3 bar. We also need this value, so we're not using the XNOR symbol. Okay, we use this symbol, but this is actually the XNOR. All right, and this circuit, the equality comparator circuit, and also the 4-bit comparator circuit, are the parallel. I hope this is the correct way to write it. Comparator.
Correct.
Correct. Okay, thank you. So this is the parallel comparator. All right. Yeah, we have E here because we have 4 XOR here, right? Okay, so this is the parallel comparator where we compare all 4 bits at once. All right. Okay. Okay, so that is the parallel comparator. There is another one where we compare bit by bit because we want to make a module like an adder. You have like a full adder module bit by bit. So we want to make the module for comparator, 1 bit comparator. Okay, and we call that comparator slice. Okay, and the terms that we use when we make a module for 1 bit is bit slice. So sometimes maybe you found in the textbook or reference book where it says bit slice comparator or bit slice adder, which means the addition or the comparison, which means the process is done bit by bit. So we call it bit slice. Okay. So this is one module for comparator. Okay, let's see. We just want to compare 1 bit A and B. When A is a 0, B is a 0, that means E is 1 because it's equal. Yeah, it's equal. When A is 0, B is 1, okay, that means L is 1. Okay, L is 1. Because A is less than B. Okay. When A is 1 and B is 0, G is 1. Okay, because A is greater than B. And if both are 1, then E is 1 because it's equal. Okay. All right. So from here, okay, we can get the equation where L is when A is A prime B because A is less than B, right? And G is when A B prime because A is bigger than B. And then E is the XNOR, okay, whether both are 0 or both are 1. So from here, from this equation, we get the circuit, and the circuit looks like this. Okay. So this is A bar, B, A, B bar. So this is A bar, B bar, A, is it? A bar B, sorry. A bar B and A B bar. And this is A bar B plus A B bar. So I hope you know how to make this to become A B plus A or B bar using the De Morgan, right? Okay. So this is the module of 1 bit comparator. Okay, the comparator slice. Okay. And then this is like the half adder stage. Okay, we only have 1 module so that we can do it 1 bit. We can do the process 1 bit, do the comparison 1 bit. But we want to repeat this module, okay, like we repeat the full adder, right? So we have to find the cascadable module. Cascadable means you can connect it, okay, like this, or like this, or like this. Okay, as long as it's cascadable. Okay, so for making it cascadable, what should we have is the E out and G out. Okay, means the cascadable test input A in A B G. I don't know how it looks like. Something like this. A E and G for input, and we have E output and G output. Okay, it looks something like this. All right. Okay. Oh, and remember, when we do comparison, we start from the MSB. So it's not like this. It's supposed to be like this. A in, B in, E in, okay, because we start from the MSB, and G in, and then E out, G out, and this is connected to another comparator slice. Okay. E out, G out, right? And this is the next bit to the MSB, and so on. Right? So let's see the condition here. Okay. E out is equal to E in, and condition of E in, and then condition of A I B I, which means the condition here, and then the XNOR condition of A and B of the current bit. Okay, which means for this bit, okay, for this comparator, okay, we are checking the XNOR of A and B and the E in, which is the E out from the previous comparator slice. So that will give the output E out. And for the G out, we are checking the G in, which is the G out from the previous comparator slice, and whether E in, the previous E in, okay, is 1, and AI BI, because we want to check G, right? So A is equal to B. It's A, B, I bar, right? So this is the conditions. Okay. E is for equal. What time? 9:49. And this is greater. Okay. All right. So as we did previously, okay, when E in is, okay, if the higher order bit, okay, this is like higher order bit, means bit on the left side. Higher order bit means it's on the left, bit on the left. Okay, if higher order bit is not equal, so E in is 0, okay, we check whether it is greater or not. So if G in is 0, means it's less. If G in is 1, means A is greater than B. Okay, if that's the case, okay, we don't care about A and B anymore. We straight, okay, get the output. Okay, the last bit, the LSB. We can go straight to the LSB, where the circuit is if G in is 0, means A is less than B. If G out is 0, means A is less than B. If G out is 1, means A is greater than B. Now, if the E in is 1, it means the bit on the left side is equal. So then we have to check the G, A, and B condition. So if G in, if all 0, which means A is less than B, okay, the previous bit that we compare, which is the bit on the left, is less, A is less than B, then we check A and B, whether it is greater or not. Okay? And if it's greater, okay, where A is 1 and B is 0, then we will output G out as 1. Okay, now let's see the example so that you can see better. Almost done, we're almost done. Okay. Let's see, A is 0, 1, 0, 1, and B is 0, 0, 1, 0. So this is 5 in decimal, and this is 2 in decimal. Okay. So A is greater than B, which means we should get, at the end, we should get E0. Okay, here we should get 0 because it's not equal. Okay, A and B is not equal, so E0 should get 0, and G0 here should get 1 because A is greater than B. All right, now let's see the process. Let's change pen. Okay, A is 0, 1, 0, 1, and B is 0, 0, 1, 0. Okay, and the condition, the initial condition here, okay, because we want to check the next the first A3 and B3 here, so the initial condition must be of E in must be 1. Okay, the initial condition of E in must be 1, because if the initial condition is 0, okay, we are not, the A and B is don't care, and we straight get the answer. So we're not gonna do that. Okay, we're not gonna set that. We're gonna set E in, the first E in is 1, so that we can compare A and B here. Now let's compare A and B at this bit. At this bit is equal. So since this bit is equal, so the E out is 1 and G is 0 because it's not greater, it's equal, right? Okay, having this condition, so since E is 1, we compare A and B. We compare A and B. And since A is bigger than B, so G is 1 and E is 0. Right? Now, E is 0 and G in 1, okay, which means we got into this condition. E is 0 and G in is 1. So now at this stage, A and B is don't care. We no longer care about A and B. We straight got the answer here. Okay. It doesn't matter what are the values here. Okay. The E and G is 0 and 1. All right. All right. So you can do, you can try another example too, where A is less than B and A is equal than B. Okay. I just want, we have like another 5 minutes. I just want to go to the last subchapter, which is the incrementer. Don't worry, we only have one slide for this. All right. So this is the incrementer. Okay, this is the incrementer. The incrementer has it's just a 4-bit increment. Like we have the original value, the input is x, which means we have x3 if it's a 4-bit, right? X3, x2, x1, and x0, and the output is y3, y2, y1, and y0. Okay, so the output y3, y2, y1, y0 is the results of x plus 1 because we just increment 1, right? And to do that, x3, x2, x1, x0 is at 1 at the LSB. Okay, at the LSB bit, we add 1. Okay, the others is just the carry. Okay, the carry. Okay, and we will get y3, y2, y1, y0. So to implement it on the circuit, we use half adder, only half adder. Okay, because we only have 2 input for each bit slice. Okay, 2 input for each adder slice. Okay, which is one the X and another one is the C, where for the first bit or for the LSB, we use input C to add 1. Okay, just like when we add 1 during 2's complement, we use input C to add 1. All right, so that is all about the case study. Okay, that is all about the case study. That is all about chapter 6. So next week we have class on Sunday and then your test on Wednesday. So class on Sunday, we're supposed to go into the sequential circuit case study. Okay, remember there are 2 types of circuit, the sequential and the combinational. We have done the combinational part. We're supposed to go into the sequential circuit. But instead of that, let's do revision on Sunday. Okay, revision for test. And then we go for the sequential circuit on Thursday. All right, everyone? Sorry, the class is
Yeah, all
quite
right.
rushed. Okay, sorry, the class today is quite rushed. Maybe you don't really have time to ask questions. So if you have any questions, you can ask in the group or ask next week during the revision class on Sunday. And yeah, I will make like last chapter, the chapter 5. I give you the slides with the handwritten annotation, but since this is a dirty handwriting, I will make it a better one and share it with you today. All right. So thank you for your time. Now is 9:59. Please get ready for the next class and have a great weekend, everyone.
Thank
See
you,
you.
doctor.